Hello friends and welcome to another lecture by Free Shiksha, where I'll discuss one of the application of derivative, which is to find the maxima and minima of a function. So let's begin with understanding what do you mean by the maximum and minimum value of a function. Of course we all know what do you mean by the maximum and minimum value, but when it comes in context of a function, how do you define it? So we define it by saying that if a function attains a maximum value at a particular point, say A, in its domain D, then the function's value at that point would be greater than or equal to the function's value throughout the domain. Okay, very simple. And similarly you have the definition for minimum value of function. So if it has a minimum value at point A in its entire domain, that means the value for the function at that point would be less than or equal to the function's value in its entire domain. Okay, then comes the term local maxima. So a function might not attain the maximum value at a particular point A, but still if at A the value of function is greater than the value at A's neighborhood, then the function has local maxima at A. So let's see this graph, and it's pretty clear looking at the graph that the function has maximum value at this point B. You have a peak here and it has a maximum value at B. But then you have two more points to consider, where if you see that the function's value at this particular point A is highest in its neighborhood, whether you take the left neighborhood or you take the right neighborhood. So the function's value at A is highest in its neighborhood. Function's value at B is also high in its neighborhood, left and right, and similarly at C. So what we say is that the function has maximum value at point B, but the function has local maxima at A, B and C, all three of the points. Similarly you have the local minima, where we say that the function might not attain the minimum value at that point A in its entire domain, but if at A the value of function is smaller than the values at A's neighborhood, then the function has local minima at A. Again, consider the same function. So if I assume that the function is attaining the lowest value at this particular point, then you have two more points here. So if you have A and you have B, and you can clearly see that the function is approaching the minimum value at B, which is smaller than the function's value in B's neighborhood, and similarly the value at A is smaller than the function's value in A's neighborhood. So we say that the function has local minima at A and B both, but it has minimum value at function A. Now the necessary condition for local maxima or minima to appear. So for a function f of x to have a local maxima or minima at some point x is equal to A, you see these two curves. You have local maxima in this particular curve and you have a local minima in this particular curve. So what is the common thing that you observe in both these curves? It's the tangent. So the tangent, if you draw at A and this point A, the common thing is that both these tangents have slope equal to 0. Okay, so that's what the condition is. The tangent to the curve at point A should have slope equal to 0. If it happens, then it qualifies for having a local maxima or minima at that point. And now since the slope of a curve is given by f prime x, which is the first derivative, so what we say is that at x is equal to A, if f prime x, that is the first derivative of x, goes 0, then it qualifies for having a local maxima or minima at A. It only qualifies. It doesn't say necessarily that it has a local maxima or minima at A. So the values of A, values of x where f prime x goes 0 are called the stationary points or values, or critical points or values. Now the point of inflection. So as I said that if you have f prime x equal to 0, it only qualifies you for having a maxima or minima at that point. It doesn't necessarily say that there will be a local maxima or minima at that point. So what else could you have is a point of inflection. So if your f prime x goes equals to 0 at some point x is equal to a, but it's not a local maxima or minima, then we say it's point of inflection. So you see this curve y equals x cube. At x is equal to 0, if you draw a tangent, it has a slope equal to 0. But you can clearly see that it's not a local maxima or minima, because at x is equal to 0, the value is not highest in its neighborhood. It should be higher than left and right both neighborhood, which is not happening here, and similarly it is not smaller than its left and right both neighborhoods. So the slope of the tangent at x is equal to 0 for f prime x, you can clearly see, is equal to 0. But still the value at x is equal to 0 is not greater or less than both the neighborhoods. Such points are called point of inflection. Now what is the final condition for local maxima or minima to appear then? If f of x is differentiable function at x is equal to a, then first a is a point of local maxima if f prime a equals 0, that's what I said, and also f prime x changes sign from positive to negative going past a. If you want to have a local minima at x is equal to a, then of course f prime a should be equal to 0 and the sign of f prime x should change from negative to positive going past a. And if the sign doesn't change, you have f prime a equal to 0, then that's your point of inflection. Let's consider this particular example. So to have a local maxima or minima, what was the necessary condition? That f prime x should be equal to 0. So let's put that. If I put f prime x equal to 0, the first derivative of f of x equals 0, I get three values of x. X equals 1, minus 1 and minus 1 upon 5. And if I plot that curve, this is how it will look like. So since you have two roots at x is equal to 1, so going past 1, the sign won't change. We start from the rightmost side with a positive curve and then it goes past 1, and since you have a square here, the sign won't change. It will go up, it will come down, then the next root is at minus 1 upon 5, so it will cut y equals 0 at minus 1 by 5, then it goes up and cuts at minus 1. That's how you plot a curve when you know the roots of that particular function. So if I draw f prime x, that's how it's gonna look like. And if I want to see how the signs are changing, so you can clearly see that going past 1, the sign is not changing, it's positive. Going past minus 1 upon 5, the sign changes from positive to negative, and going past minus 1, the sign changes from negative to positive. So you have a local maxima at minus 1 by 5, you have a local minima at minus 1, and you have a point of inflection at 1. So that's all we had for the maxima and minima. In the next lecture, we'll consider how do you test the local maxima and local minima conditions with the help of higher order derivatives, and some more properties of maxima and minima we'll also consider. If you have any doubts regarding this particular lecture, you can comment below the video and we'll be more than happy to answer those queries. Thank you so much.